Hi everyone, so welcome to the IME 470 online class. Today is March the 25th. Let's continue our topic in duality LP, which is lecture 7. Let me stop my video here and let me share my screen. Okay, I need to open a Word here. Okay, very good. First of all, I need to clarify the mistake that I made last time in the solver, which is here. Let me see. Last time, so we introduced how to directly read the dual solution from the primal optimal tableau, and the method is here. So if it's standard, meaning that the maximum the constraint is less than or equal to, then yj simply equals to the corresponding coefficient equals to the coefficient of the corresponding slack or excess variable. And if it's maximum greater than or equal to, or minimum less than or equal to, then that equals to the negative coefficient here. Let me get this annotate. Where's annotate here? I'm gonna let you see this one. Otherwise, some of you may not know what I'm doing, because this really, you have to switch here and there, And if the constraint type is equal, then if it's a maximum problem, then it is the coefficient of aj, where aj is the corresponding artificial variable by the bigger method. If it's a main problem, then it's going to be negative coefficient of aj. And we showed the example here. Right, I stopped here, and I remember I made a mistake in the last meeting. The reasons because where it is? Oh, it's here. The reasons because I set up these constraints wrongly. Today, let's redo it to see whether it's correct or not. Where it is? Data. Okay, so to show that I'm not cheating, I'm gonna make all of them to be 0. Okay, I can simply delete it. They're the same actually. Okay, so we're gonna run the solver. Let me see. F1 to F2, and I'm gonna minimize this one. So last time what I did wrong is that I forgot to set up this one, the main constraints. So what you're gonna do is that you're gonna set, okay, anyway, let's delete everything. Let's start from the beginning. Make my life easier. So what we're gonna do is that, first of all, we have the constraints that, oops, sorry, it's not this slide, it's this slide. Yes, first of all, I have everything here. I have everything here as greater than or equal to 0, because here already, -3, -2, -5. So I only need to put a greater than or equal to 0. And the second thing is that because y1 is greater than or equal to 0, but y2 is less than or equal to 0. So I have to define this correspondingly. So this one is greater than or equal to 0, meaning that y1 is greater than or equal to 0. And y2 here is less than or equal to 0. And click OK. Y3, it doesn't matter. Why? Because y3, my constraint sign here is equal to URS. Okay. So by the way, this slide is also corrected. Now, make sure you do not choose this option, make unconstrained variable non-negative. Why? Because I do have a constraint, I do have a variable 3, y3, which could be negative, right? Or could be positive. So that if I click this one, it's gonna force y3 to be positive, non-negative. So I'm not gonna click this one, and then I'm gonna choose solve. And you can see the solutions right here. And I'm gonna show why these solutions or these numbers are correct. First of all, you can see these two numbers are the same. This is a verification of the strong duality theorem. And from the simplex method, we know that it should be equal to this value. How to verify it? Simple. I'm gonna directly calculate it, 565 over 23. And you can see they're exactly the same. Okay. Now let me insert another one. Now I'm gonna calculate y1, y2, y3 to see whether these claims are correct or not. Let me draw a box here. So I claim y1, y2, y3 equal to this. And let me go back. I need to check whether they're really correct. So 51 over 23. And you can see these two numbers are the same. And then let's see, the second number is negative 58 over 23. Again, the same. The third number is 9/23. Again, the same. Then yes, it tells you that the method we use here, which means we directly read their solutions from the optimal simplex tableau of the LP or primal LP is correct. Okay. Any questions? I think I set up mute for all others. So if you do have a question, please feel free directly to unmute yourself and directly ask me. Oops, where are you guys? Oh, I cannot see. Oh, it's here. Any questions here? Don't forget to unmute yourself, otherwise I cannot hear you. No? Okay. Now let's continue. Today I'm going to introduce two very important things. They are complementary slackness. And I'm going to introduce two parts of the complementary slackness. By the way, complementary slackness is another, I would say, like a variant of the duality theorem, both strong, and especially for the strong duality theorem. To see what is that, let's first have an example. So this is my prime LP. And this example we have used tons of times. Remember, since let's say lecture 4, let me open lecture 4. Where's my lecture 4? In which the very first simplex method algorithm, I used this one. So here's lecture 4, and you can see, I think they're the same. Yes, exactly. Oh no, this but it doesn't matter because this is just multiply -1 both sides. Exactly the same solution. And we know that the optimal solution should be what? Should be this. 7/3, 4/3, 0, 0, 2, right? We know it. Okay. We pretend that we don't know. Let's see. Anything interesting gonna happen? And I have a look at this solution. First of all, it's very easy to see that this solution is indeed a basic feasible solution. What I'm talking about is this, as the solution that x1 equal to 1, x2, okay, let me write it down in this way. So x1, x2, x3, x4, x4, x5. And this solution gives you x1 equal to 1, x2 0, sorry, x2 is 2. I didn't see the x2 here. x3 equal to 0, x4 equals to 2, and x5 equals to 0. Okay, and this is indeed a basic feasible solution. Why? Because it's pivoted. I pivot with respect to x1, 2, and 4. You can clearly see it. It's pivoted. Okay. Now let's input the C's. C1, C2, C3, C4, C5. Doesn't matter because all of them are 0. So C1, what I'm talking about is this. This is C1, this one. This is C1 equals to 2, C2 equals to 3, and I don't have a C3, 4, 5, so of course they're 0. So 2, 3, and 0, 0, 0. Okay. Another thing that I have is what? Is the B. So I have B1 equals to 5, B2 equals to 6, B3 equal to 1. Okay. So let's input the B's. B1, B2, B3, and I have B1 equal to 5, B2 equals to 6, and B3 equals to 1. Okay. Then what I'm gonna do is this. I define the coefficients. Be careful. I'm saying coefficients of x1, x3, x4, and x5 to be y1, y2, y3. I just define them. You know, I denote them, or I name this one to be y1. I name this one to be y2. I name this one to be sorry, this is a typo. This should be y3. I name this one to be y3. And let's see what's gonna happen. By the way, be very careful that these y1, y2, y3 are the coefficients of x3, 4, 5, okay? They're not the value. Do not confuse the coefficient with the value. They are very different. And let's see, if I define y1, y2, y3 in this way, what's going to happen? So from the table, I know that y1 equals to 5/3. And, okay, 5/3 equals to 5/3, which is 1 point. Seriously? Let's see, number. And the y2 equals to 0, and the y3 equals to -1/3, right? Okay, it's because of the digit. So for example, I can show more digits. So, whoa, I forgot this baby. Okay. Here we go. So, they're indeed 1 over 3, 5 over 3. And I'm going to do what? I'm going to check CTX, meaning, the dot product. C1, x1 plus C2, x2 plus C3, x3, blah, blah, plus C5, x5. So I'm going to have CT x. This is equal to what? Okay, or let me write it in this way. C dot x. This is either, be careful, this is dot product, okay? And then this is equal to Excel now have a very good function, sum product. This is equal to this, and C. And we see this is equal to 8, the same here. Now let me calculate. BT equals to Y. BT dot product Y. So I have BT is here, B is here, dot product, sum product of BT and Y. And again, it is 8. Then it's interesting. By the way, do you have any questions? I remember when I first learned it in the very beginning, I got confused with the strong duality theorem. I was thinking, hey, is there anything wrong? Do you have any questions here? Any, kind of like the feeling you may feel something's abnormal or something's wrong. Recall the strong duality theorem, okay? So the strong duality theorem tells you that if X star is the optimal solution to this LP, usually we define this one as the primal, and Y star is the optimal solution to this LP, then I must have CTX star equals to BTY. But have a look at here, this example. What is that? Where it is? Here we go. This XT, I mean, it's just a random basic feasible solution. It's not optimal because we know that the optimal solution should be equal to this, right? Should it be, where it is? Should it be equal to 7 over 3, 4 over 3, 0, 0, 2. But here, the solution considered as 1, 2, 0, 2, 1, 2, 2, 2, 0, which is absolutely not the optimal solution. But I just told you that, well, you still have CTX equal to BTY. Then is there anything wrong? Because the strong duality theorem tells you that if that's the case, you should kind of like, like X star is the optimal and Y star is the optimal, right? And so what is the problem here? Think about it. Be careful. Be carefully think about it. Again, the Y1, Y2, and this is Y3. Y3 are just a definition, okay? They are not necessarily feasible to the dual LP. In other words, they are not necessarily qualified to be this Y. This is a hint. And you know what? Indeed, this conclusion is general. I'm talking about if X is a basic feasible solution, and I denote the coefficients here in this pivoted, of course, tableau as the Y's, then I must have CTX equal to BTY. Here we go. Here we go. So this means I define these Yi's to be, the corresponding to be the coefficient of the snack variables in a pivoted tableau. Again, be careful. I said a pivoted tableau. This means first, of course, it's pivoted. Second, it's not necessarily to be optimal solution. It's just any pivoted solution, okay? So we have the property that if X is a basic feasible solution to the primal LP, then we must have, under this definition, we must have CTX equals to BTY. No matter this X is optimal or not. Let me change a color. What color you think is good? Let me change it from a yellow color. That's a good point of online teaching. It's easy to change different colors, and I will not forget my markers. Otherwise, I always forgot my markers. Okay, so the problem is how to kind of like resolve the issue with the strong duality theorem, because the strong duality theorem tells you that X and Y looks like needs to be optimal solutions. But here I said, no, they don't have to be optimal solutions. What is the problem? Okay, the problem is here, that if x is not optimal, say for example here, this x, yes, it's a basic feasible solution, but it's not optimal, then, where it is, if x is not optimal to the primal LP, then the y you find here, it's not feasible to the dual LP. It's not feasible to this problem at all. Why? Because you can easily prove this, because suppose it's feasible, okay? Suppose this y is feasible. Then by the weak duality theorem, this is the definition. This x star is the maximal, is the optimal solution to this one. In other words, my CTX must be less than or equal to, here I should be strictly less than. Why? Because I already know this x is not optimal. So that I must have CTX strictly less than CTX star. Then by the strong duality theorem, we have what? We have CTX star equals to BTY star, where this X star is the optimal solution to the primal LP, and this Y star is the optimal solution to the dual LP. And then, because I assumed that Y is feasible. If Y is feasible to the dual LP, then I must have what? I must have BTY strictly less than BTY star strictly less than BTY. Why? Because the reason is because I know the Y is feasible to this problem and the Y is not optimal. So I must have this conclusion. Then this tells you what? This tells you that CTX is less than BTY, which is what? Which is contradictory to our knowledge, the condition that CTX should be equal to BTY. So that this tells you that if X is not optimal, although it's a basic feasible solution, then use this definition Y, it's not feasible to the dual LP. In other words, if it's under this form, you're gonna see that at least one of the Y's gonna be negative, which is infeasible. And what if X is possible? What if X is optimal then? So if X is optimal to the primal LP, then the Y is gonna be complementary optimal to the dual LP. Since Y is optimal, then of course Y is feasible. So this is also easily to be shown by the strong, I think here's the strong duality theorem. First of all, you have what? You have CTX equal to BTY. This is what? This is the strong duality theorem, okay? Be careful here, X equals to X star actually, because X is assumed to be optimal. And what? And by the weak duality, and by the definition, we know that BTY star must be, excuse me, less than or equal to BTY. For what reason? Because this Y star is the minimum, right? The optimal solution to this problem. So for any feasible solution Y, I must have BTY less than or equal to BTY star. Okay, now I have what? I also have this property that CTX equal to BTY, so that if you plug in everything, you're gonna see what? CTX equal to BTY star, CTX equal to BTY. This tells you what? This tells you that BT's Y star must be equal to BTY. And this B is a general B, okay, an arbitrary B, not some specific B's. So this tells you there's only one possibility, that Y equals to Y star, meaning that Y is optimal to the dual LP. Okay, so again, let's review this part a little bit. First, we observe, where it is, what goes so fast? Okay, so first we realize, we observe a fact here from this example, and which is CTX equal to BTY, where this X is a random, basic solution. Give me a second. Sorry, I have to move to the order. Okay, where this is the any basic feasible solution. Now, we know the property that this is actually a general conclusion, that if X is a BFS to the primal LP, any problem, not necessarily this problem, then I must have CTX equal to BTY, no matter X is optimal or not, but X must be a basic feasible solution, okay? That means the tableau must be a pivoted tableau. Then the two further conclusions are, if X is not optimal to the primal LP, then Y is not feasible. if y is not feasible to the dual LP, if x is optimal to the primal LP, then this y will correspondingly be complementary optimal. I wrote the complementary in the parentheses is because you don't have to add this complementary. I use this complementary just to show you the relationship, the logic relationship. Then y is optimal to the dual LP. Let's see an example. Just continue the previous example. So previously we have verified here. I check this x, which is a basic feasible solution, but it's not optimal to the primal LP, right? And y is what? The corresponding y is this, because I can directly read it, And I've already checked that CTX equal to BTY equal to 8, which is here. Okay, now let's see. X is not optimal. We know it, because the optimal solution should be what? 7/3, 4/3, 0, 0, 2, right? So we know X is not optimal. Let's check whether Y is really feasible to the dual LP. The conclusion is not. Why? Because your Y3 equal to -1/3. But what is your constraints here? You must have Y1, Y2, Y3 greater than or equal to 0. So that Y1, what I'm talking about is this one. So that this solution, Y1 equal to 4/3, 5/3, Y2 equal to 0, Y3 equals to -1/3 is not feasible to the dual at all. See it? So this shows this part, okay? If X is not optimal, then Y is not feasible. Then let's see the second part. If X is optimal, so here, if X is optimal, meaning that X indeed equals to this, 7/3, 4/3, 0, 0, 2, and correspondingly, my Y, by definition, is 4/3, 1/3 is 0. And what do you have? If you substitute here, yeah, that's a good point. Here, I can directly substitute. 7/3, 4, please, number. Where's the number here? 7/3, 4/3, 0, 0, 0, 0, 2, right? Okay, let's show a bit more digits. Okay, and if I put the Y here, equal to 4/3, 1/3, and 0, you see? They're again equal. First. Second, I want to show you that this Y is indeed optimal to the dual problem. To this end, let me formulate the dual problem here. Y1, Y2, Y3, OBJ. Okay, let me be lazy. 5, 6, 1. This is the objective function. So for the coefficients here is 1, 2, -1, and 2, 1, 1. Okay. Now I can use this equal to sum of product of y's versus the coefficients here. And I have two constraints, CS1, CS2. Come on, CS. Okay, good. That's beautiful. CS2. And this equal to sum of product of y's and this coefficient minus what? Minus 2. And this equal to sum of product of y versus this one and minus 3. Okay, then let me solve it. Where's my solver? Data solver. So I'm gonna I'm gonna minimize this one. B20 is B20, and then changing variables are here. And let's choose simplex. And indeed here, everything is non-negative. I'm talking about the y's. And I'm gonna add constraints, which are these two must be greater than or equal to 0. And solve it. See it? 1, 3 to 3, 0, 3 to 3, 0. The same here. This tells you what? This tells you, okay, this y is indeed optimal to the corresponding dual LP. Any questions? Any questions? So this example is just to verify these constraints. These conclusions. Okay. No question? Okay, now let's have a look at the second part of the complementary slackness. Here, again, we define in this way, the same way that the definition, the coefficients of the corresponding slack variables are y1 to ym, okay? And again, this acts as any, basic feasible solution, not necessarily optimal. First, we can easily observe a fact that si yi must be 0 for any I. And this S means the corresponding slack variables, okay? Do you know why? First of all, do not confuse the coefficient with the variable value. So Si means the real value, the true value of these slack variables. How would you know Si's? You're gonna see here, for example. You're gonna see here, okay? For example, this x3 is actually, what? Something here, right? A slack variable for constraint 1, right? So here I can see x3 equal to 0, x4 equal to also 0, x5 equal to 2. These are the values, okay? Meaning the S1, S2, S3 here, okay? And these are what? Are there, 4/3, 1/3, and 0. These are their coefficients. Coefficients and the values are two different things, okay? So I claim that yi must be 0. Forever it is 0. Why? The multiplication forever be 0. Why? Because I'm going to discuss two cases. If Si is a non-basic variable, then by definition, non-basic variables are 0. So of course, Si times yi equal to 0. The second case is Si is a basic variable. Then for a basic variable, what's going to happen? In a pivoted tableau, remember the simplex tableau method? In a pivoted tableau, the coefficients in the first row, in the 0, for all basic variables must be what? Must be 0. Remember? So that if S is the basic variable, then I must have the corresponding yi equal to 0. So no matter which case, Si and yi, one of them must be 0. That's why forever I have Si, yi equal to 0. This is, very easy. And this acts as any basic feasible solutions. Then the question is, what if the X is optimal? Right? Because here I just claimed any basic feasible solution. It doesn't have to be optimal. If X is optimal, will there be any interesting things? Like, for example, here in the first part of the complementary slackness, what do we have? If X is optimal, then Y is corresponding or Y is complementary optimal to the duality. Do we have something similar like this one? The question is yes, which leads to the very, very famous and important complementary slackness theorem. First of all, let me introduce my system. So my system is this. I still assume my primal LP is in this way, and the corresponding dual LP is, of course, in this way. Then to write it make this coefficient, this constraint sign to be equal, I'm gonna add the corresponding slack variables. And here I'm gonna subtract the corresponding excess variables. Now, again, let X be any feasible solution to the primal LP, and Y be any feasible solution to the dual LP, okay? And by the way, here I'm talking about this solution and this solution. So in this case, I do have a X greater than or equal to 0, and also S is greater than or equal to 0 later. Then the interesting thing is what? The interesting thing is X is a primal optimal and Y is dual optimal if and only if you have this property, that Si, Yi equal to 0, and meanwhile, Ej, Xj equal to 0. The corresponding Ej, Xj is what? The corresponding Ej, Sj is the coefficients here in the dual LP, okay? So this is gonna be X1, this is gonna be X, let me see, I should be Xn, not n, because in the dual LP, I should have n constraints. And the corresponding here is gonna be E1, and here is gonna be En, okay? So That is where EJ and XJ from. And SJ, YJ is what? As the values from the optimal, sorry, from the tableau of the primal LP. EJ, XJ as the corresponding dual LP, the tableau. And again, not necessarily optimal, but this just tells you that X, first of all, X and Y, they are pairs. If one is optimal, the other must be optimal. The second thing, this tells you that they are optimal, the pair X and Y are optimal to the primal and to the dual LP if and only if Si, Yi equal to 0, and also EJ, XJ equal to 0 for all I and for all J, okay? M means how many constraints I have in the primal LP, and N means how many decision variables I have. So N is the dimension of X. Correspondingly, again, because a constraint in the primal LP is corresponding to what? Is corresponding to a dual variable. So that in the dual LP, I must have what? I must have N variables and N constraints. Okay. So let's see how to. Oops, where it is? I don't know why. Okay, now it's 25. Yes, it's page 25. Let's have a look. What does that mean? Check this example again. So I have, let me write it down. Give me 1 second. Let me write it down. So for the primal LP, I have what? Let me write it in this way. P25. Let me make what's so ugly? Primal LP, dual LP. Okay. For the primal LP, what I have is this: maximum 2x1 plus 3x2. Oops. Subject to x1 plus 2x2 less than or equal to 5. The second constraint, 2x1 plus x2 less than or equal to 6. And the third constraint is negative x1 plus x2 as less than or equal to 1. And of course, I have everything greater than or equal to 0. Okay, so this is my primal LP, and my dual LP is gonna be mean of 5y1 plus 6y2 plus y3, and subject to y1 plus 2y2 minus y3 greater than or equal to 2, and the second constraint is 2y1 plus y2 plus y3. y3 is greater than or equal to 3, and then the last thing is y1, y2 greater than or equal to 0, right? Okay. So in order to make this one to be this form, I'm gonna do it this way. So I'm gonna change all the constraint signs to be equal. To this end, I'm gonna do this plus S1, so this becomes equal. I'm lazy, let me copy and paste. Let me choose my favorite blue color. Okay, so come on. Okay, let me disable the touch board. Okay, then this one gonna be x2 and this one gonna be s3. And of course, here I have S1, S1, S2, S3 greater than or equal to 0. Let me use the blue color again to indicate that there's something, there are the slack variables. And here, something similar here. In order to make this sign to be equal, I'm gonna minus E1 equal to 0, equal to 2. And here similar. Minus E2 equal to 3. And correspondingly, I'm going to add E1, E2 greater than or equals to 0. Okay, here we go. So from lecture 4, I have already known what? The optimal tableau of the primal LP, which is this, right? Okay, now let's see. Here, from here, I have x1 equal to 7/3, x2 equal to 4/3. X3 and X4s are not here. That means they are non-basic variables. That means they're 0. And finally, my finally my S3, S3 equals to 2 is here. And correspondingly, I can get to the Y's. First of all, I've already solved the Y here, right? You just, I'm lazy to show the simplex tableau, but the solution here for Y1 is 4/3, Y2 is 1/3, and Y3 is 0, right? Question, how can you calculate E1 and E2? Because I do have E1 and E2. How would you calculate E1 and E2? Simple. As though you already know this, let me use a box here, box. As you already know Y1, Y2, and Y3, right? So the next job is what? The next job is nothing but to substitute this. Let me give a little bit of distance here. Okay, here I have dot. Anyway. So I'm gonna substitute Y1 equal to 4/3 plus 2 times 1/3 minus 0 minus E2 equal to 2. And you know what? 4/3 plus 2/3 equal to what? Equal to 2 already, so E1 equal to 0. The second thing similar, 2 times 4/3 plus 1/3 plus 0 minus E3, E2 equals to 3. And this gives you what? This gives you simply, let me see, 8/3 plus 1/3 is 9/3 equal to 3. So again, my E2 equal to 0. See it? So this gives you what? Indeed, I have E1, E2 equal to 0. And you can verify this relationship. See? S1 times Y1 equal to 0. S1 is this. Okay, let me draw the box again. First, let me clear. Okay, so this is, oops. Box, draw the box. So this is S1 times Y1, this equal to 0, see it? And let me choose different colors. And this is S2 equal to Y times Y2, see, again equal to 0. And S3, let me choose, for example, the blue color. S3 is 2 times Y3, again it's 0, see it? And you can do the same for axis, for E1 and X1. This is super easy because my E1, E2 already equal to 0. So that no matter what X1, X2, they are 0. See? And this tells you that, yes, the conclusion that we, why? Oh, okay, I have to go back to this. The conclusion that we draw, which is the complementary slackness theorem here, is correct for this example. Any questions here? No? Again, you can unmute yourself so that everybody can hear you, okay? Otherwise, I cannot hear you. Okay. Now let's see one more example, which is the last example of this lecture. Another interesting thing for the complementary slackness theorem is that if I just know the optimal solution, I don't know the tableau, okay? I just know the optimal solution. Use the complementary slackness theorem, I can easily solve the dual LP. Why? Let's have a look at this example. So pretending that I don't have this tableau, but I do have the optimal solution to the primal LP as 7/3 4/3 002. Now I want to ask, what is the solution to the dual problem? First of all, what is the optimal value to the dual problem? This is very easy. Why? By the strong duality theorem, okay? You just, it tells you that the optimal value of this problem should be equal to the optimal value to this problem. So that you just need to substitute, x1 equal to 7/3, x2 equal to 4/3 to this objective function. Then you can get the optimal value equal to 26/3. Which should be the same as this one, right? Now I'm asking for the optimal solution of the y's. How to do it? Well, by the complementary slackness theorem, I have what? I must have y3 equal to 0, e1 equal to 0, and e2 equal to 0. Why? Because have a look at this. Where it is? Draw the box. Because look, my x1, x2 are non-zero, and my this is what? This is E3 is all. Sorry, S3 is also non-zero. By complementary slackness, what do we have? We say that how can I go back here? We say that if x is prime optimal and y is going to be dual optimal, if and only if si y must be 0 for all i's, and ej xj must be 0 for all j's, right? Now the problem is that your x1 is already non-zero. This tells you what? This tells you your e1 must be 0, right? Similar, x2 is also non-zero. This tells you your e2 must be 0. Similar, your s3 is already non-zero. This tells you what? This tells you your y3 must be non-zero. Otherwise, how would you guarantee this? Otherwise, how can you guarantee that siyi and ejyj are 0, right? So I immediately get y3 equal to 0, e1 equal to 0, and e2 equal to 0. Now I'm gonna plug in this conclusion or drawings. Let me draw a picture. The box again. I'm gonna plug in this one to here. Arrow. How do you draw arrow here? Plugging this information to the dual LP. Then you immediately have what? You immediately have y1 plus 2y2 equal to 2 because y3 equal to 0 and e1 equal to 0. And then from the second one is 2y1 plus 2y1 plus y2 equal to 3. Why? Because y3 equal to 0 and e2 equal to 0. So you just simply solve this equation. This equation is actually the set of the equations. And I believe everybody knows how to solve this this set of equations, right? And you're gonna easily get y1 equal to 4/3, and wait, I think this solution is it's correct. You're gonna easily get y1 equal to 4/3, y2 equal to 1/3, and y3 equal to 0, e1 equal to 0, and e2 equal to 0, which is the same as what we just solved here. See, 4/3, 1/3, and 0. That's everything about the lecture 7 and also the lecture of today. Any questions? No? Let me go back. Okay, now you can see me. I hope we means both you and me, we can get adapted to this online studying or teaching. Actually, a lot of fun here. In some parts, it's a little bit more complex, but in other parts, it's kind of like easier than using the whiteboard and also the markers. If you have any questions, please feel free to contact me. And again, I will hold my office hours, okay? Finally, do not forget your homework, which is due next, let me see, next Monday or Friday? Next Friday. And stay safe. See you again. Thank you. Bye-bye.